Hi, my name is Sarah Blackwell. I'm a graduate student at the University of Georgia, and I'm going to tell you a little bit about a project I'm currently working on that will be part of my thesis work. So the setting for this project is the 1-0 trisection of the complex projective plane. So this is a decomposition of CP2 into 3-4 balls. That's what the 0 means. And the triple intersection of these 4 balls is a torus. That's what the 1 means. And these 3 curves on the torus this is supposed to be a diagram representing CP2, where the curves tell you how to connect 2 handles to get back to CP2. But here there's just 1 curve of each color. What I could do is I could draw parallel copies of each of these curves, and that would not change what this diagram represents. And so then if you view this torus as a square with the edges identified, you get this picture in the middle, and with that looks very grid-like. And if you look at each of these colors pairwise, you see that you really have 3 grids: a pink, a blue grid, a green, pink grid, and a blue, green grid. And then if you put 0 or 2 dots in every row, column, and diagonal, I'm going to call that a triple knot grid diagram. So why is it a knot grid diagram? Well, if you connect all of the dots with a crossing convention, that the way that these are drawn, you're always going to cross vertically over horizontally, then you get 3 knots. And one thing you could do is you could cap off these knots or maybe links with discs and get a surface in CP2. So that's pretty cool, but we could go even further. So grid diagrams also really naturally represent Legendrian knots. So how you do this is you take each of these knots, you turn them 45 degrees counterclockwise, and then you put in cusps as needed. And this gives you a Legendrian front. And so because Legendrians then are really natural boundary conditions for Lagrangian surfaces, then kind of a natural question to ask is, well, could we fill these 3 Legendrian links with disks and get some kind of Lagrangian-like surface in CP2? So the idea here is we're kind of coming up with these combinatorial Lagrangian surfaces. So this is kind of the motivating question of this project. And so here is more precisely kind of what I just said. So the conjecture is that for every triple grid diagram, where each component is a max TB Legendrian unknot, there is a Lagrangian in CP2, which intersects the pieces of the trisection as specified by the diagram. TB means Thurston-Benneken number, and the reason I say max TB unknot here is because that's the only Legendrian unknot that can be filled with a disk. So a much stronger conjecture then is that every Lagrangian in CP2 is isotopic, maybe Hamiltonian, maybe Lagrangian isotopic to one given by a triple grid diagram. So that's pretty strong, maybe more of a question than a conjecture. But a weaker conjecture is that every connected oriented triple grid diagram in which each grid is a Legendrian unlink of max TB Legendrians gives a torus. And I realized I forgot to say earlier that there is a way of orienting these grid diagrams, and that tells you whether the surface you get is oriented or orientable or non-orientable. So that's what oriented means here. And the reason that you would expect this conjecture to be true is that the only oriented embedded Lagrangian in CP2 is a torus. And so I have some evidence towards these conjectures. So I have examples of the standard embedded RP2 and an immersed S2 with 1 double point. And I also have not found any embedded oriented surfaces with genus not equal to 1. So that's good. That's what you would expect. So this is what I've been thinking about. But there's lots of other things you could do with these triple grid diagrams. So you could define, some invariants. So you could define something called a minimal triple grid number. So a minimal triple grid number for a smooth link L would be the smallest n such that there exists an n by n triple grid diagram with L as one of its links. And so you could also do this with Legendrian links or with a triple of Legendrian links, etc. And so here, for sake of time, I won't read through, but here are just some results that I've come up with so far. One thing that's interesting is all of these numbers are the same as the regular grid number except the hop link. The regular grid number of the hop link is 4, but here it's 6, so they're not the same. And then here's just a few more results that I have that you can pause and read if you're interested. And so that's what I've been thinking about. Thanks to the organizers for letting me speak, and I will see you all at the conference.